Well, good evening, and welcome to 16 Nearly Impossible Issues for Evolutionists to Answer. Isn't that a mouthful? If you want to contact me later, there is my email address. I'll leave that up there. By the way, how many people here have tried to do any battle with evolutionists in the past? Any at all, or is this just an introductory for you? Anybody at all? Yeah, I know you have. Turn it off, please. Okay. Well, we'll just make this an introductory then. Can I have those, please turn off any pagers and cell phones and so forth. All right. The main objective is we're going to be focusing on sketches of 16 issues that are mostly scientific. And the claim I have is that the evolutionist responses fall short. Now, in the last 2 years of school, I learned a considerable number of things which I've since put to good use. And one of them was in an education class. I learned about the 4 philosophical schools of thought. Frankly, it had nothing to do with education, but it did open my eyes towards these. The first one is absolutism, which means somebody said so. The second was, which is empiricism, is that somebody tested it. The third is pragmatism, which says that somebody discovered that something works. And the fourth is existentialism, which means somebody found that something occurred. Now, for this talk, I suggest that the best school of thought is empiricism. Now, what is an empiricist? An empiricist is a person who just goes with the evidence wherever it is, and if new evidence comes in, he modifies the conclusions that he previously made. Good evening. I saw this statement on the Backyard Skeptics site a couple months ago. We need empirical evidence of any claim to accept it as true. I agree with that statement. Not to be an existentialist or not to be an evidentialist, but I do believe the statement when it comes to the matter of what constitutes truth. We're not in the business of fairy tales or making up things as we go. Let me mention this busy chart called empiricism, the dispassionate interchange. That is, the only things that should matter are the facts themselves and the logic behind them. Not politics, not emotion, just the facts. We often associate empiricism, and rightly so, with the scientific method. We have a model, which is our theory, versus the reality, which is the practical or the pragmatic aspect. And we will collect, measure, observe, test data. Laboratories preferred. And we'll also test it out in the field to see whether or not it holds up. Also, for the more sophisticated, we get to correlating and cross-correlating. And all these are done under the ever-present questioning skeptic eye. And we might even have some skeptics here, and if we do, I welcome your questions in due season. Now, somebody may come along and throw us new data, new facts, new ways of thinking about things and so forth, in which case, as empiricists, we're willing to modify our conclusions as these things happen to come in. We repeat, in other words, and we keep revisiting this endlessly. Now, in empiricism, there's no such thing as 100% or 0%. You might find those in the absolutist world, perhaps, but here we're only dealing with 0%, a little bit higher than that, or less than 100. You may have a very high probability, you may have a very low probability, you may have something in the middle. Let me say something also about probabilities. What we have these days is that the impossible becomes the possible the plausible, the plausible the probable, and the probable the certain. This is not science. Show me why something that's impossible can become possible before going on any further. Otherwise, we're saying that we believe in miracles over science. There are also non-empirical categories. That is, they're not amenable to examination over and over and over again in the laboratory or otherwise. These would include the historical, that is, the things that have already occurred, the spiritual, that would include anything that would be said to be invisible but still there, not having any mass, and the unsensed, the things that we cannot measure and cross-correlate and so forth with any instruments or with our own 5 senses. the non-empirical categories are not subject to the laws of science. They might be subject to other things, like the courtroom, but not here. We have to distinguish between on the other. So, for example, if somebody came along and gives you a, well, what about this and what about that, you need to assess whether or not it is empirical, that is, it can be tested over and over, or it can't. If you try to make scientific arguments based upon the things that you never could in the first place, you might run into trouble. Have you ever seen this quote before? Especially the last part that says, though each was partly in the right and all were in the wrong. We might have thought this would have come from Rudyard Kipling, but it actually came from John Godfrey Sachs, The Blind Man and the Elephant. It's often in kids' tales from a famous Indian legend. We have our perceptions. Our perceptions are due and fraught with error. Other people might have a better eye for some things than we do, and we might have a better eye than other people in other areas. We have to take that into account and be very humble with what we come to the table with. Also, we don't know 1,000,000% about anything said by the person who had more patents than anybody in the United States. If he could say something like that, where would we fall? The general scientific principle is that verified scientific laws don't displace other verified scientific laws. So if somebody comes along and says, I have this newfangled theory out here, and oh, by the way, it's governed by this and so laws, don't let the statement stand where it is. Ask, what about the things that we know are true for everything else? What about those? My problem oftentimes is that people never revisit the things that we have known for hundreds or thousands of years. Instead, we're swayed. By the way, in saying the new science better agree with the old science, I was there to see the talk of Stephen Wolfram on 1 February 2003. You might recall there was a shuttle disaster that occurred that same day. And 3 skeptical professors of his alma mater, Caltech, said, the new science better agree with the old science. We'll keep revisiting that topic again and again and again. Another preliminary is that extrapolation is similar to interpolation. But first, can anybody tell me what extrapolation, and can anybody tell me what interpolation mean? Anybody remember from their high school class when they were interpolating logarithms, or anybody at all? Nobody at all. Okay. Well, interpolation is when we're trying to fit a bunch of points between 2 known points. There's no universal way of determining that, even for things that look like they should fit pretty well together. Extrapolation is trying to find points that are beyond the points that we already have available. Extrapolation, as I say at the bottom, is much more likely to encourage mischief than interpolation, especially back into the unobservable, unrepeatable past. Have you heard a number of people say, especially in the science community, that we know that thus and so occurred thousands, millions, billions of years ago? Ask a silly question. How do you know that? Where is the evidence, not the theory, where's the actual evidence that things in fact did occur that way, not that they could have occurred that way? I'm going to use a universal definition of evolution. Evolution just simply means change. It's commonplace for people to think that evolutionists are only dealing with biology. That hasn't always been the case, and I still don't think it is. It can deal with any number of things. Usually it means an unguided process gets us from point A to point B. It could be chemical. It could be stellar. It could be cosmological. It could be linguistic. It could even be societal, as well as being biological. Anything that would experience that sort of thing. So I'm going to use that definition of evolution rather than only the biological for the purposes of this talk. In fact, there's a better way of saying it. Universal evolution says that everything is getting better and better and better all the time. I have some interesting challenges for that when they come due. One other is review of thermodynamics. I have a couple of textbooks right here. The blue one is my undergraduate, and the green one is my graduate textbooks in thermodynamics. There are 3 laws of thermodynamics, which are nicely summarized in the opening pages of the green textbook. The first law says I'll just read the stuff in red. The best you could do is break even. The second is you can only break even into absolute zero. And the third one is you can't reach absolute zero. There's also a zeroth law that says you must play the game. And so therefore the conclusion, if nothing intervenes, is you must lose. This is what we have if we don't have anything else to guide us. Now we can finally embark on the 16 issues themselves. The first one is, why does anything exist? The second one is, did the universe always exist? The third one is, did the universe cause itself to exist? The fourth one is, how can the universe avoid heat death? Each one of these will be covered one at a time. The fifth one is, how can any material travel faster than the speed of light? The sixth one is, what is the origin, transportation, and distribution of carbon? A hardly covered topic. Seventh, how do any stars exist? Eighth, how do moons form? Ninth, what is the ongoing source of comets, long-term comets in particular? 10th, how do any elements heavier than iron exist? 11th, how do peptide bonds exist? 12th, how do proteins have only L, or left-handed amino acids? 13, what turn non-life into life? 14, how does metamorphosis occur? 15, how do major morphological changes occur? 16, what creates information from gibberish? Now I'll try to keep things as simple as possible. Please reserve your questions to the end, however, if you don't mind. Let's start with that first one. Why does anything exist? Well, if nothing does exist, we don't have any space, we don't have any material, people, a meaning, we have nothing. It's been said that from nothing, nothing comes. I like to point to Roget's pocket thesaurus as maybe the place to start. Has anybody used Roget's pocket thesaurus before? Raise your hands if you've used it. Thank you. Where might you have used this treasury of synonyms and antonyms that can study the language? Where have you used it? Huh?
English class.
English class? Yeah, what for?
Looking at a different word.
Yeah, shades of meanings of one word. Do you happen to know what topic number 1 in the thesaurus is without peeking? Well, now you can peek. Look at it. Look at the screen and see what category number 1 is. Existence. I don't think that's any accident. And also, it stands to reason that if the first category is existence, that the last categories might have to do with the possible causes of existence. So it bookends the thesaurus. You have an interesting time looking at the thesaurus now and with new sets of eyes rather than just simply a scattered bunch of topics. Not only why does anything exist, which by the way the evolutionists run from because they really don't have any answers, they can't even really begin the discussion, but why this particular amount of mass? It's been said that we have 10 to the 80th atoms. You don't have any idea how big 10 to the 80th is? You'd have to multiply our national debt by itself, about 5 or 6 times before you can get to that answer. But why not 10 to the 79th? Why not 10 to the 81st? How do we know these things? And why isn't it one of those other figures or a host of others? And why this particular distribution? The distribution will be an argument I will use again and again and again throughout this presentation, both in the universe and on the Earth. Now, there's lately been a thing that's been called quantum fluctuations. I don't suppose any of you have heard of that, have you? No? Well, that's the idea that nothing turns into everything. I'm sorry, it doesn't. The thought is that nothing turns into a particle and an antiparticle, and that we can come back together again if we care to. Is that really what would happen? No, because if a particle and an antiparticle came together, you can check it out with some physics later, it would form energy. Now, if you repeat the process over and over and over again, you have a violation of that first law of thermodynamics. Remember we said that was, you can't win, the best you can do is break even? In more formal terms, it is that mass energy is neither created nor destroyed. But if you could take nothing and create particles and cause them to come into each other and form energy, you could form endless amounts of energy from nothing. That's not what is even being touted. Instead, an already existing energy field, for which they have no explanation, is the source of these particles, and then they can come back into the energy field. But that's the problem. They can't explain the existence of the energy field. That's just a little, I won't say any more about quantum fluctuations, but for those who are watching who are interested, that might answer your questions about how could nothing turn into everything. It doesn't. The second question I want to ask is, did the universe always exist? I take a show of hands. Yes? How many believe it always existed? No. How many believe it didn't always exist? No opinion. Okay, you don't have any opinion. Okay. Okay. That's terrific. I'm going to say no. Why? Now, notice I'm not going to refer to anything other than scientific arguments, which is important here because those who would say that things like the Bible are not relevant, that they're false by fiat, are going to say, well, I don't take your book as being worth anything. Well, it's important for these people to show that there are scientific arguments to counter them. Meet them where they are, like what Paul did in Athens. No, because otherwise we wouldn't be here. Everything would have already dissipated an infinite time ago, if it had always existed. So we have two choices for the universe. It's either open or it's closed. If it's open, it allows outside entities like God to come in. But of course, they can't allow a defined foot in the door, so they would say it's closed. Well, in that case, there's no escape from the effects of the thermodynamics. We'll cover that in a topic, 2 topics from now. I used these arguments to troubleshoot with an atheist a few weeks ago and showed him within a total of 9 questions that his answers were inconsistent with each other. In other words, he can't use them as a scientific argument. I think he got a shock by seeing that. Next question is, did the universe cause itself to exist? Now, how many think that it did? Yes? Anybody think the universe came into existence? I'm sorry, caused itself to exist? No? How many believe that it did not cause itself to exist? Okay, and we got the rest of them that don't want to hold up their hands or don't have an opinion. Okay. I'm going to say no to that also. By the way, I've had people say yes to that first question, did the universe always exist? And then when I show them that it didn't always exist, they'll come along to this topic, and they'll answer yes to this question, even though those 2 answers are inconsistent with each other. No, else, catch this logic. It's a little bit long, but a little bit to digest, but just catch this logic. If it did cause itself to exist, then it would have had to have existed before it existed to cause itself to exist. Or, another way is the universe would have had to have existed and not existed at the same time and in the same way. This is a logical contradiction. Hope you can put on your bifocals in case you can't read that. I'll try to help you through this. We can take those issues 1, 2, and 3 to a cosmological argument. Cosmological argument is an argument to show that there must have been something outside the universe that is the cause of its existence rather than something within, or that it always existed. So by application of the first law, does the universe exist? Yes. By application of the second law, did the universe always exist? No. And by logic, did the universe cause itself to exist? No. So therefore, I have ruled out all material causes with those few issues. That's it, because everything else has to be a subset thereof. There are no material causes to the universe. That only leaves 2 possibilities. Either the universe had no cause, in which case the argument is unscientific. It is actually existentialism, which is one of the earlier philosophical schools that we mentioned earlier. And we might as well talk about such issues in China, India, or wherever in the East where they discuss things in those terms. Or the universe still has a cause, but it must be immaterial. Now, consider the following list of possible immaterial causes. Fairies, leprechauns, gnomes, my favorite nowadays, flying spaghetti monster, God. You add to the list. Oh, by the way, only God even has any testimony. So, if somebody says to me that they think that my line of reasoning is no better than that of a flying spaghetti monster, I will turn to that individual, hopefully charitably, and say, I don't believe in a flying spaghetti monster. You do. And I don't have any more arguments at that point. It's not the creationists who believe in the flying spaghetti monster. Not at all. We can also rearrange them a bit. Does the universe exist? No. Well, then you're in an insane asylum, so we'll say yes. Does the universe have a cause? No. That would be unscientific. Yes. This is a troubleshooting steps, in other words. Is the cause material or immaterial? Well, if it's material, did it always exist? No, because otherwise it would violate the second law of thermodynamics. Did the universe cause itself to exist? No, because otherwise it would violate logic. In fact, did anything cause itself to exist? Has anybody ever seen anything cause itself to exist? Well, if not any one thing caused itself to exist, then why should we assume that the universe, which is supposedly the sum of all those things, caused itself to exist? It makes as much sense, or nonsense. How can the universe avoid heat death? Well, heat death is the dissipation of the heat in the universe. Like, for example, if you turn on your refrigerator, what happens in a refrigerator? What's the basic function of a refrigerator? Somebody, anybody. Keep things cold. Well, how does it do that? It's a little pump that works in there that causes the heat to go out and keeps the lack of heat inside. What happens when you turn off the pump? Goes back to the way things were. Like the mob would say, room temperature. It's a consequence of the second law of thermodynamics that one day there won't be any motivation to do anything on the part of physical objects. It will all have been dissipated. That is the inevitable consequence if nothing intervenes. It's a consequence of what is called Le Chatillier's principle. If something is in equilibrium, there's nothing to take place. If it's out of equilibrium, then Le Chatillier's principle guarantees that we bring things back to a stasis, that is, where things are calm, peaceable, whatever, until the next shock comes along. But it will not stop until it's converged to the point of bringing things to a point of stasis. The universe, however, is continuing to wind down. It's increasing in entropy or disorder according to the second law. So the end point is the complete dissipation of the universe, and everything will be brought to a complete deterioration from which it has no return. Is there any hope for a constant or steady state universe? Well, if there is, the new science better agree with the old science, and the old science is the thermodynamics are still there. How can any material travel faster than the speed of light? Well, maybe you didn't think any could. Neither did I. However, despite the fact that there's no observation of any such behavior, there are people who would posit there is a Big Bang. That is, there was this infinitesimal where everything was concentrated in a space that's arbitrarily small but not zero, and for some reason flung itself out. There's a problem with that, however, and that is, unless things do travel faster than the speed of light, there's no way to get it to agree with the fact that the universe is already at 2.7 degrees Kelvin, which, by the way, is mighty cold. It's very, very close to absolute zero. How would anyone know that that's true, even? And what about the time factor? I've seen other figures besides 10 to the minus 31 seconds. Why not 10 to the minus 32 seconds? Or why not 10 to the minus 30 seconds? And why only one time? Why not a bunch of times? And there's also a thing that's called the graceful exit problem. That is, when it speeds up very, very quickly, what brings it back down again to the way it is? Why this only is one split? There is no physics behind it. It's just imagination. There is a group known as Reasons to Believe. I don't know if any of you have heard about this group. It's somewhat of a bane as far as I'm concerned. Unfortunately, I didn't get to talk to Hugh Ross himself, but their staff I did for weeks, and they have no answer to this issue. I think they wish they did, and they have no answer to the next issue. What is the origin, transportation, and distribution of carbon? I'd like some help from the audience. What examples of carbon do you see or not see that this figure is illustrating? One example at a time, please. Anybody want to give me one? And especially some of the people who have not participated yet. Anybody? Bazell, you want to give one?
Is that volcanic shale?
I'm going to take another answer. Anybody else? Huh? Diamond is one, the one on the right side. That's certainly an example of carbon. It's an unstable form, too. All your diamonds are going to dissipate one day. Any other examples in that figure? There's plenty there. Yes.
Coal.
Coal. That's what you were trying to identify. What else? Yes.
Any organic life.
Any organic life. All that stuff that looks like fuzz. Anything else? Anything else you could see or not see? Anything above that stuff?
Try.
Huh?
Take another try.
Okay, you could get some redemption here, yeah?
Carbon dioxide.
Carbon dioxide, yeah, you've seen this before, okay. All right, anything else? I have never yet gotten anybody to give me the next answer, by the way. I've given this talk many times. Anything? How about carbon monoxide? How about methane? There are any number of gaseous compounds that contain carbon. Somebody even ventured, last time I talked, as to calcium carbonate. In other words, limestone. Maybe that's running around somewhere in this. That's an interesting example. My question isn't that there's carbon throughout the universe or on the Earth. My question is, what's the origin of it in the first place? That was a problem supposedly solved by the triple alpha process near the bottom of that slide. And what might you ask is the triple alpha process? Well, hydrogen from stars, that's the next topic, fuse to form helium. That's a process we do know occurs. However, from there it should stop because, among other things, helium is a noble gas. There are also mass gaps at element weights 5 and 8, which this book, as illustrated, points out. Not as good as it could, but it does point them out. How would you get across the mass gaps of 5 and 8? Well, the triple alpha process says, furthermore, that the two helium atoms, each with mass of 4, come together, and even though they form a transitory species of that forbidden mass 8, before that transitory species can fly apart in 10 to the minus 15 seconds, a third one comes along and gives us our mass of 12. It can only take place at one nuclear resonance, only in red giant stars, and be disseminated only by a supernova. Let me put it in shirt sleeve English. It's an extremely improbable process. Not impossible, but improbable. My question at this point is, how is the carbon going to get to here? Our sun does not qualify as a red giant star. It never has been one, and even when it gets to that stage, it's still not going to be big enough to cause a supernova to disseminate that carbon. Where's the nearest red giant star now? Anybody want to take any guess how many light years away we think it is? Anybody want to just throw out a number? No? I won't shoot you. Just anybody? No? Okay. Minimum of 33, maybe as many as 40. Ask yourself, is the carbon from such a star that explodes in a supernova, is all that carbon going to jet its way in one direction towards the Earth so that we will form miles deep, thousands of miles long, solid coal beds several places throughout the Earth? Even if you had a number of these, would they be jetting all their carbon to this place? Well, haven't seen it yet. By the way, I would call that, let's see if I can find the place there. I would call that dark matter. Not the kind they're talking about, of course. This is the place in the periodic table where, have you seen the periodic table in a chemistry class by any chance? Yes, yes, yes. Can anybody identify where carbon is in that periodic table? It's a little small to read, but can you get an idea?
It's near the top right.
It's near the top right. Where, can you see anything? Is it too small to see?
It's to the right of the very top brown one.
It's to the left of boron. I'm sorry, it's to the right of boron. In other words, the second element in on the second row towards the right. Right, that's where it is. We'll get to the periodic table to discuss something else later. So, in summary, this is what the triple alpha process amounts to. We'll have that in the handouts later, I guess. Now, another hypothesis is that we had red giant star in the volume of the known solar system. Well, I haven't seen any evidence for that, but let the evidence come forth if it's there. But the next problem I have is, isn't a supernova going to be blasting everything out in all directions anyway? Where is it going to accumulate in any one place? The transportation and distribution problems I've just outlined are the ones that I have never seen anybody discuss at all. I doubt you're going to find them anywhere either. You might, but I doubt it. This is a figure of the world's coal deposits. Notice how irregularly spaced they are from each other. In the United States, you might notice the area in the Appalachians, which runs all the way down to Mexico. There's also a couple of stretches in the Midwest. There's a stretch from Montana that leads into Canada. There are also a number of seams in Russia, as well as a big one over there in Australia. Notice that there's hardly anything in South America where there should be plenty of vegetation to form coal beds. This is a problem. If things operated uniformly, then we should expect to see coal uniformly scattered all over the place and not economically viable or mineable. But this is what's the case instead. How is that going to be also explained? That's the distribution problem in particular. I said I would come to that topic again and again, and here it is. Next, how do any stars exist? Let's suppose that we have all of the mass confined to an infinitesimal volume, which we discussed earlier, and then there is a Big Bang. What is going to become of the particles that emerge from the Big Bang? The space is going to expand out, and what's going to happen with the particles in it? According to Newton's first law, what will happen? Any guesses? They will keep moving away from each other, and moving, and moving, and never stop moving away from each other. What does it take to get a star, supposedly? The particles have to be coming together, and together, and together, and all in their own, mind you. We have a hard enough time trying to compress gases as it is on the Earth for solidification, as in liquefaction, as in liquid or solid form for use. We have to have a specific compression device to enable the solidification or the liquefaction. And by the way, once you remove the device, then the former gas now returns back to being a gas again. It doesn't stay there without that compression device being there. Now ask yourself, if you're trying to form a star, how are you going to get the particles not only to come together and come together and come together on their own, when actually, in a Big Bang, they're going the other way, and at massive speeds too. And even if you were to get them there, how are you going to get them to stay together without a compression device around it? By the way, the compression devices that we have are much smaller than a star too. See, this is the sort of problem that I come to the table with, and I ask, where is the explanation? Where are the scientific data for it? But I'm an empiricist. If you want to come forth with an explanation that has merit, be my guest. There's a flip side, however, and that is, let's assume for the moment that the count of the number of stars in the universe, how we get there I don't know, is about 10 to the 21st. That's another one of those things you can take the national debt, multiply it a couple of times before you can ever get to that kind of a figure. No, I don't know where it comes from. And let's assume that we even give a generous 20 billion years for the process. Most of the big bangers come up with, I think, is 13.7 billion. But we'll even give it much more than that. That would mean, on average, that we'd have to be producing 50 billion stars every single year for every one of those 20 billion years. Somehow, I don't remember seeing in the newspapers or on the radio or television anything about us meeting our quota of 50 billion stars last year. Have you seen anything like this? Neither have I. In fact, as I recall, we're excited if we can only even see one star being produced, let alone this. Now, it could be that the 50 billion per year is, being as it's an average, it could be that there were many much more formed in the past and that they trailed off, or it could be going the other way a little bit in the past and then it trails off. The point is, it's still an average of 50 billion stars. 50 billion stars every single year. Nope, there's got to be a better way than that. Next, how do moons form? This is one of my favorites. Let's assume we even have the stars and the planets that are orbiting around them. 8 around us, 9 if you want to count Pluto. I got a silly question. How do you get solid moons from gaseous planets? By blasting the planet. Can anybody tell me any of the gaseous planets out there? Any? They're all the big ones. Saturn's one of them. Any others? Jupiter's another one. There's scientists right here. Huh? Uranus and Neptune. Any others? No. All right. Those are the 4. They've got most of the moons, too. Those are all gaseous giant planets. Some much bigger than others, Jupiter being the largest. Well, I don't know of any way to blast a gaseous planet to get a moon to come out of it. Not only that, but even if you were to hit the planet, more than likely, much more than likely, whatever you try to blast the planet with, the planet would absorb it. And that would be the end of the attempt. That would be a right fact. You might have even seen some of those in the recent past where something blasted into the surface, or I guess the atmosphere. But we also have a moon associated with our Earth. What about it? Well, same thing. Suppose you had something that came along, maybe moon-sized to begin with, and it were to impact the Earth. What would be the most likely thing that would happen? It would just stay in the Earth. That would be it. You'd have to have a lot of velocity behind it. Well, let's suppose you do. Let's suppose that it actually causes things to come out. Well, the first thing that's likely to happen is they'll fly up in the air and then they'll come back down to the Earth and then that's it. Okay, suppose you have some more velocity. Well, then they have to reach the point what is called Roche's limit. I don't suppose you know what Roche's limit is, do you? All right, those are the things associated with tidal forces. That is, if something comes too close to the Earth and it's held together only by gravity, it will shatter apart. That's what's been hypothesized for our own moon when it supposedly is going to come back towards the Earth. It will shatter. We don't shatter apart because we're held together by electrical forces, not by gravitational forces. So, if it can even get past Roche's limit, which is what? 1 to 2% away from the center of the Earth? Then it has the following possibilities. It can either escape the Earth altogether, which means it'll never be orbiting around the Earth, or it may still not have enough velocity to reach even orbital velocity, in which case it'll still come crashing back to the Earth, and your moon experiment is once again over. Or it will reach orbital velocity. That's that magic Goldilocks velocity. But there's a problem. You also would have to have something coming along perpendicular to it coming out of the Earth, if it's straight out of the Earth, exerting enough force, but not too much, to cause it to actually orbit. It's a delicate balancing act. By the way, we don't know of any forces that would impact the moon at that point to cause it to go into an orbit. So I would say that hitting the Earth to cause a moon to come out of it doesn't fly. What about capturing? That is, there was a moon that came along and a planet just happened to capture it. Well, Many people in the scientific community have regarded this now as being too coincidental, but I've got a different problem if that's still not too much. Why aren't there other tries and the evidence thereof? Why don't we see other kinds of objects having made a go at it? We get scared enough as it is if we see a meteor coming in our direction. Witness what happened last year. Think what would happen if we saw a moon coming in our direction. Might be a problem. So there are no plausible theories. Take a look at this statement. Since tidal forces overwhelm the gravity that might hold the satellite together within this Roche limit, no large satellite can gravitationally coalesce out of smaller particles within that limit. Translation, even if you got a bunch of loose particles, they won't stick together. And even if they did stick together, that's not the way the moon exists now. The moon exists as a compact body. There's no known force that will cause things to compactify by themselves, especially in deep outer space. I think I'm going to skip this slide, but it's an answer to the question of why can't there be a capture from the standpoint of somebody who advocates another theory. If somebody wants to see that slide later, I'll be happy to show it. What is the ongoing source of comets? There are two kinds of comets. There's the short-term comets like Halley's Comet, which have a period, goes from the outer extent of the universe around the sun and back, typically, of 200 years or less. Halley's is about 75 to 76 years. They can be explained by two things. One of them is called the Kuiper Belt, and the other is the interplanetary disk. This is the source of such things. It's the longer-term comets that cause the problems. Some of them have the same source as probably the short-term, but it's those other ones that we can't explain, where they came from. In other words, they're still there, they're still coming in, and typically a comet will one day lose all of its mass and or fall into the sun or have some other such fate. They don't gain mass. So, what is the hypothesis for the source of these long-term comets? The Oort cloud, spelled O-O-R-T. And what might you ask is an Oort cloud? It's like a dirty snowball automatic pitcher, pitching out comets, conveniently, of course, to make up for the ones that are lost. There is no evidence for the existence of an actual Oort cloud. There are some indications there might be something out there, but there's certainly not anything that we can point to say, now there's our Oort cloud, and it's the object that's causing all the comets to appear. But I'm an empiricist. If you want to show me a good Oort cloud, then we can talk. This is a topic I love to talk about. How do any elements heavier than iron exist? I'm going to refer back to our periodic table. Now, you might notice in the upper left-hand corner is what element? Anybody? What's that say? Element number 1 is what? Hydrogen's correct. And all the way down in the bottom are all those elements that somehow or another we were able to overcome the normal forces to get. They're all artificial, by the way, after uranium, and they're all radioactive after bismuth. I want to focus on the middle of the 4th row. And if you can see that, you see it says 21, 2, 3, 4, all the way up to 30. Can you see that just a little bit maybe? Okay. Near the middle of it is Fe. What element is that? Iron. Good, good. It's element 26. It's bounded by 25, which is manganese on one side, and 27, which is cobalt on the other. That's the focus of this topic. Here is a chart that I saw in my modern physics textbook, the one at the bottom here. It's called the average binding energy per nucleon curve. Where's the maximum in that curve? What element?
Iron.
Iron, precisely. What's the meaning of this curve? Iron is more favored to form than any other element is favored to form. If we start with hydrogen, which would be on the left side, then we can get to fusion, although there's some ripples there. You notice that has to do with that carbon formation and other things. But finally we might get there by fusion, fusing things together. And there it would end, because everything else beyond that is less stable to form than iron is. This curve shows that the only way you can get the other elements between them is by fission of already existing elements, such as, what's that one on the right side? Got a big U there. Uranium, that's right. How do we get the other elements? The hypothesis is a supernova. It comes to work its magic again. Or maybe not, because remember what a supernova does. A supernova blasts everything out in every direction, such that none of those elements would be economically viable either. And yet we see plenty of cobalt, nickel, copper, zinc, and so forth. And don't forget gold and silver, they're in there too, as well as mercury and a few others that you might recognize. All the elements from atomic number 26 at iron to atomic number 92 uranium. That's a lot of elements there, between 92 and going backwards to 26. All those are supposedly formed by a supernova. It remains to be seen whether or not a supernova could even do such a thing, but I have that problem, as I just mentioned, distribution. That's a summary of what I just explained there. Here's a chart of the world's mineral deposits. If we were to take a closer look, which we can't right now, we'll see that there are blank spots, like for example in Greenland, Siberia, Eastern South America, Eastern Africa, and the like. Now some of these might not have been explored enough to see whether or not there are any minerals there. But I would imagine that places in Africa we certainly might have, and especially in the United States. I'm kind of surprised there aren't too many mineral deposits in the Rocky Mountain region where we supposedly have gold and silver and the like. Most of the precious materials are located in only a handful of spots, like South Africa, Russia, China, political hotspots, unfortunately for the rest of us. The point I'm making is that they are unevenly distributed. If it were happening according to the Big Bang hypothesis, we should see things more or less uniformly scattered again so that they're not economically mineable or viable. How do peptide bonds exist? Let me introduce the figure first before going to mine because the colors are different. The black atoms, that's what those are carbon atoms. You can see them throughout. The white atoms are hydrogen atoms. The blue atoms are nitrogen atoms. And finally, the red atoms are oxygen atoms. Now, let me take one of these and illustrate, if I may. I wish I had bigger models, but this is the best. Now, my colors are different. Take that into account. This is a model of an amino acid. This is the central carbon atom. To one side of it is a nitrogen atom, which is connected to two hydrogen atoms. It forms what is called an amine group. Can you think of any household compounds that sound like amine?
Ammonia.
Ammonia, very good. Ammonia would have a third hydrogen instead of the carbon. Now, on the other side is a carboxylic acid. Here is the carbon, here's the doubly bonded oxygen, here's the singly bonded oxygen and the hydrogen. COOH, carboxylic acid. Formic acid is an example of one. It's what gives certain kinds of ants their sting. To the top in this figure is a hydrogen atom, and to the bottom, to the right, is what is called a functional group. This is a model of an amino acid. Now, what we see in the figure is where two of these have already come together. What do you suppose that molecule below that condensation of what is called glycine, what do you suppose that molecule is? Water is correct. Have you ever heard that tale that all life came from a warm little pond? Just how is that going to occur when a water molecule must drop out, not be absorbed by the amino acids? This is a problem. I'll illustrate also in this next slide. You see that on one side we have our amino acid, glycine. Can you see the OH on the right side then? Can you see that? That's the oxygen and the hydrogen from the carboxylic acid. Can you see that? Okay. And you see on the other side the amine group of the next amino acid. It's got the nitrogen and the two hydrogens. Can you see that? That OH, or hydroxyl group, combines with one of the hydrogens to send off the water. And then it forms, as you see, what is called a peptide bond. That is the beginning of the formation of a protein. If we repeat that process over and over and over again, where R1, R2, and so forth are the same or maybe different functional groups, we'll form a chain. All proteins have this same form. They are all linear chains with no branching. So I've got a silly question. If you need two of these to lose a water molecule, how's that going to happen in the open? Well, we've already covered the case that it can't be in water. How these two would ever find each other if there's no water in the first place, I don't know. All you would have left is dry land. And what can happen with dry land? You'll have either an oxidizing atmosphere, which may be either oxygen or something else that would have the same effect, or a reducing atmosphere. For the sake of argument, let me just say oxygen for the oxidizing agent. If we have an oxidizing atmosphere, the oxygen will break the bonds and maybe the amino acids too. On the other hand, if we don't have any oxygen, like in some primitive atmosphere, we have, instead of reducing atmosphere, we have no ozone. And then the UV rays come and they destroy the bonds and maybe the amino acids. Meaning, peptide bonds do not form out in the open. They can't for those reasons. And without any peptide bonds, there's no proteins, there's no enzymes, there's no life. And by the way, without biochemistry, it's what? An amino world. Think about that one. Bad joke, bad joke. Okay. Now, the next topic is the same amino acids can be either left-handed or right-handed. Let me demonstrate by example. Can you see by looking at the figure and or what I'm holding up here that these two molecules are mirror images of each other? Can you see that? Can you draw a mirror through that? Does anybody have any trouble seeing that? Okay. We'll designate one of them to be L, left-handed, what's called lever rotatory, and the other to be right-handed, or D, which is called dexter rotatory. Now, you can see that also in the figure. You see the carboxylic acid is up in red towards the apex there, the carbon's in the middle, the hydrogen's at the other extreme, the amine group over here on the outside, and the R group, the functionals, on the inside. That's one way of drawing it. You can see that those are mirror images. But what you can't do, is stick one of these on top of the other so that they all match. It's just not possible to do. That's the best you can hope for. It's not a match. Notice that these are in reverse order. The best you can hope for is 2 out of 4 plus the carbon atom in the middle. And that's owed to the orientation, the spatial orientation. It's not possible to stick one on top of the other. Therefore, the two molecules are different molecules. They have the same melting point, boiling point, refractive index, vapor pressure, chemical reactivity, density. The only way you can tell them apart by themselves is by putting them under a thing that's called plane polarized light. You've heard of Polaroid cameras? Same idea. One of them will rotate plane polarized light by so many degrees in one direction, and the other by the same number of degrees in the other direction. You could perhaps form compounds with other elements to form other pairs that you could easily see which is which by the fact that the number of degrees spread is bigger. This is what we call non-superimposable mirror image compounds. Kind of a big long word, but what it means is they look like that. Sometimes they have other names if you go into your organic chemistry textbooks like I have right here. They're called stereoisomers, enantiomers, chiral compounds. You can also even have them in the inorganics. The probability of formation, however, in the laboratory from neutral ingredients, neutral environment, neutral energy source, everything's neutral, is 50-50. 50% left, 50% right. You could get other things to come along and maybe perturb that a little bit, like soil clays, maybe by 1%, or the Murchison meteorite that landed on the Earth on 27 September 1969 in Australia, which is a lot bigger difference between the two. But it will not be what we see in proteins. In proteins, only the left-handed appear. Every amino acid in every protein of every species is only left-handed. There are no right-handed ones in proteins. We're saving questions to the end. Okay? Isaac Asimov, in a paper that I read many years ago, had no explanation for this. He just simply said, well, it happened one way or the other. And I would have asked Mr. Asimov, or Dr. Asimov, over the entire face of the globe, this is what happened? Only the left-handed ones appeared everywhere when they form equally well in the laboratory, and that's the controlled conditions? There are amino acids of the D form in other structures, like bacterial cell walls. They keep the enzymes from destroying the bacteria. In fact, the bacteria, if they ever see one of these, will try to turn it into a right-handed one into a left-handed one and digest it. That is, if they can digest it at all. I can also mention, in passing, that as a math exercise, which you can do in high school, although I haven't seen any, you can actually measure the bond angles. Like, say, for example, if we took the two red ones here and the central one in the middle, we can measure what it is if they got the same components. The answer turns out to be, as you see, check your trigonometry textbooks, the arc cosine of minus 1/3, which is approximately 109 degrees, 28 minutes, 16 seconds. If you measure it, you don't need any more than Euclidean geometry and the law of cosines to actually get the answer. So it can be done. We didn't see about it until we were in college. Although when I saw it, I said we should have seen this in high school because we had the tools to do it. Now, if you don't have equal components, for example, ones that do would include methane, carbon tetrachloride, carbon tetrafluoride, and the like, where it is exactly that, then we can measure what kind of an R group, functional group we have by the distortion. That is, it will be an unequal bond from the rest of them. I'd like to read a sentence out of my sophomore organic chemistry textbook that you see the picture of in the upper right-hand corner. It's on page 236. Listen to the first few sentences before I get to the punchline. Indeed, we deal with optically active, that's what they call them, substances to an extent we may not realize. We eat optically active bread and optically active meat, live in houses, wear clothes, and read books made of optically active cellulose. The proteins that make up our muscles and other tissues, the glycogen in our liver and in our blood, the enzymes and hormones that enable us to grow and that regulate our bodily processes, all these are optically active. Naturally occurring compounds are optically active because the enzymes that bring about their formation, and often the raw materials from which they are made, are themselves optically active. As to the origin of the optically active compounds, we can only speculate. The situation is no better now than it was when this book was being written in 1972. And the problem was known for more than 100 years before that. In other words, we've made no progress whatsoever to discover why these things should be this way, when in the laboratory they always form, for all intents and purposes, a 50-50 mixture. And it never happens that way with species. Never. Next, what turned non-life into life? Suppose I gave you a dead dog, freshly killed, dead for just a few days, but dead long enough. One small task, Hercules, breathe life into the dog. I've given you all that it has, the heart, the liver, the lungs, the spleen, the nervous system, the brain. I've given you all that it has. Just Breathe life into it. What's the matter? Is this not a small task? Aren't you Hercules? Well, maybe the problem is much bigger. So consider, if we can't breathe life into a dead dog, what makes us think that we can breathe life into materials made into a dead dog? Not only that, but we really only have hydrogen to start with, or maybe just that infinitesimal from the Big Bang. There is no spontaneous generation. There is no Goldschmidt hopeful monster. And no, we don't have sufficiently developed models for RNA doing all the work. That's still a hypothesis. Life comes from life. That's all we've ever known. And Pasteur was the one who demonstrated it. Next, how does metamorphosis occur? There are two different kinds. One of them is amphibian and the other is insect. I'll deal with the latter in one aspect of it. Here's a typical diagram of a complete metamorphosis. I'll even give anybody who wants to challenge it 3 of the 4 stages. I'll give you that adults can form eggs. Eggs can form larvae, and larvae can form pupa. How they do, we don't know, but I'll just give you those for the moment. Would somebody please tell me how that pupa, in its mushy state, with no control of its own destiny, turns into an adult? I've been waiting for this kind of an answer, really. I have. I'm not dissuading anything at all. I just don't know of anybody that's produced any. And by the way, I have seen quotes, even from the recent past, where young Earth creationists, old Earth creationists, and evolutionists have all conceded it's a mystery. Ignorance is no answer either. We can't just say, well, I don't know. We'll just wait. Okay, very well. If you want to take things that way, I'll wait. And wait. And wait. Till you come up with something forthcoming. Until then, it's just a hypothesis, whatever you produce. It better also meet the criteria of being testable, observable, repeatable in the questioning eye of the skeptic, cross-correlated and correlated. It better match all those things. You know, we can sit there as long as we want. We'll even have our notebooks out there, and we'll test it all we want to, as long as we're alive to make the tests. Meanwhile, it's still a mystery. Consider that.
You might want to look at metamorphosis. Most insects, about 87%, undergo a complete metamorphosis. That is, a larva, such as a caterpillar, builds a cocoon or chrysalis around itself. Its body inside then disintegrates into a thick pulp-like liquid. Days, weeks, or months later, the adult insect emerges, one that is dramatically different, amazingly capable, and often beautiful, such as a butterfly. The food, habitat, and behavior of the larva are so different from those of the adult, it's hard to imagine. What mutations could improve a larva? Certainly none that destroyed its nerves, muscles, eyes, brain, and most other organs, as occurs within the cocoon. So even if the larva improved, it later ends up as mush. From the evolutionary standpoint, liquefying complex organs is a giant step in the wrong direction. Millions of changes inside the thick liquid never produce something survivable or advantageous in the outside world until the adult completely forms. How did the genetic material for both larva and adult develop? Which came first, the larva or the adult? What mutations could transform a crawling larva into a flying monarch butterfly that can accurately navigate 3,000 miles using a brain the size of a head of a pin? Indeed, why should a larva evolve in the first place? Because it can't reproduce.
That was John David Lehman. Next, how do major morphological changes occur? I find that interesting because the word morphological means changes. It's kind of like saying the Rio Grande River or the personal identification number. Here's a busy chart to show the things that would have to take place to get from first a fish to an amphibian. You'd have to go from no metamorphosis to its own kind of metamorphosis. The heart would have to go from 2-chambered to 3. To go from an amphibian to a reptile, you'd have to go from metamorphosis back to no metamorphosis. In other words, it would have to lose the metamorphosis that it gained. The fertilization has to go from external to internal. If you go from a reptile to a bird, you have to go from cold-blooded to warm-blooded. It's from scales to feathers. If you go from a reptile to a mammal, notice the diagonal line, you'd also have to go from cold-blooded to warm-blooded, but also the scales that had to turn instead into hair. And if you want to pursue some alternative of bird going to mammal, instead the wings would have to go to hands, paws, and hooves, and the feathers to hair. Not one of these transitions has any hope right now of being solved. Nothing even close. Now you might argue, well, you might have many different kinds of fishes, and you'd have fish, and so forth. But at some point, it would have to transition to an amphibian for the scheme to work. And it's at the point of the transitions that I'm referring to, not what might have come before that point.
Well, never mind, evolutionists still insist that feathers evolved from reptile scales, specifically dinosaur scales. And to prove the point, they say that feathers and scales are so similar you can hardly tell them apart. Have you noticed that? One of the first people to say this was Gerhard Heilmann back in 1927. In his book, The Origin of Birds, he says the most striking peculiarity of birds is their plumage, which apparently has nothing at all in common with the scaly covering of reptiles. So much more surprising is it, on examining these structures in the microscope, to learn that the feather is nothing but a further development of the scale. Alfred Romer, very distinguished evolutionist, says birds have been called glorified reptiles. Feathers are in reality almost their only distinctive feature. And he says, although these structures seem quite different from the horny scales that cover a reptile's body, the difference is in reality not very great. Well, you can look in your Encarta encyclopedia, if you have one on your computer, look up feathers, and they will confidently declare that the feather is a horny outgrowth of skin peculiar to the bird, but similar in structure and origin to the scales of fish and reptiles. So I thought we'd do a little test. I had a laboratory technician that worked for me. They had a pet boa constrictor. And I said, hey, the next time that little rascal sheds its skin, why don't you bring it on in and we'll look at it in the microscope, because I understand you can hardly tell a reptile scale from a feather. And so she did. She waited, and when this little rascal shed his skin, and by the way, I want to point out that no snakes were destroyed to do this study. We waited until they shed naturally. She brought the skin in, we put it under the microscope, and we magnified it. And this is what a boa constrictor scale looks like here. You can see the others around it. And as the evolutionists have told us, if you look at them in the microscope at least, they are remarkably similar to a feather. So then I took a picture of a feather, and I want you to see if you can tell the difference. So you may want to clean your glasses or something right now. If you got this one in mind, okay? If you get confused, just look at the top. It'll tell you which is which. Okay, that's the scale. This is a feather. What do you think? Should I go back and forth? You got it down? Or I mean, why do they say they're similar when they're absolutely not similar? In fact, I'll go further than that. They are totally different. Their mature structure is dissimilar, their function is dissimilar, their embryological development is dissimilar, their mechanism of growth is dissimilar, their mechanism of replacement is dissimilar, their chemical composition is dissimilar. And let's just look at the obvious. Scales are like folds in drapery, like drapery pleats. It's all one sheet. That's like when a reptile sheds scales. He doesn't shed them one at a time or two at a time, does he? The whole thing comes off as one sheet. In fact, reptiles typically have two layers, won't they? An outer layer and an under layer. When they shed the outer layer, then the under layer is exposed. Why do they do that, by the way? Why do they shed their skin? Because they're growing. Now, I want you to think about this. You get a box through the mail, and you're wondering what's in the box. You open up the box, you know what's in the box? A bigger box. So you shed the outer layer because the under layer is bigger. You got to think about that a while. Let's look at that boa constrictor skin. The tail's in the direction of the arrow. So to your upper right, that would be the tail. I don't know, quarter of a mile up there or something like that at this magnification. And you can see the scales are arranged in rows, sort of on the bias with the long axis of the snake. If we get a hold of the right side and flip it over like the page in a book, this is what the underside of the skin looks like. And so now the tail's in the direction to the upper left corner. And again, for those of you in the cheaper seats, let's magnify this a bit. This is where one scale just fit right underneath here. It fit right in there, so when the skin pulled off, that scale pulled right out of that pocket, like taking your hand out of a glove. And that's the way the scales are put together, is one continuous sheet. Now, feathers are completely different. Feathers grow out of follicles, just like hair. Hair grows out of a hair follicle. Feathers grow out of a feather follicle. But I'm here to tell you there's no such thing as a scale follicle. Now, what is a follicle as it relates to feathers and hair? It's a tube-like depression in the skin. You see it here. Goes down deep in the skin. All of the growth occurs in the bottom in what's called a growth collar. The feather grows out sort of looking like a thick hair. And when it comes out of to the surface of the skin, it all unfolds to make the feather. This is the way the feather follicle looks down in the skin. All of the growth is occurring here. And the feather's alive at this point, but as it makes all of its parts, it dies. It goes through a programmed cell death so that the feather that emerges from the skin is completely dead. This is how it all develops. Inside the shell here, we have what we call a pen feather. If you peel this shell away, you can see that this is the growth region at the bottom. The shaft goes up along the backside there, and then the barbs grow off this growth ring, and those little barbs get longer and longer. They grow from each side and meet at the other side. When the feather comes out of the follicle, this cylinder opens up, the barbs all swing down, and you get this big broad feather out of a hole in the skin that's not much bigger than the shaft. And that's the way each feather grows from living cells, goes through a programmed cell death, and rises up out of the follicle in that way.
It's David Menton. Final topic tonight is what creates information from gibberish. If you ever had a communication class, you might remember something like this, that communication requires a sender tuned to a receiver tuned to the sender, and a medium that promotes greater than it interferes with communication. Also, you may introduce or have introduced filters. That's not going to be part of this discussion. Suppose I have a sequence of numbers in a row. How do I tell whether that sequence is more or less random, or that it has some pattern to it? Well, I won't go into the mathematical part of it, but let me just say that there are ways of measuring it. One of them is called an autocorrelation function, measures for the pseudo-randomness. And the glorification of it is called the ambiguity function. And where can I find information from this? Well, good signal processing books have information. Also, this book called Skolnick's Radar Handbook, which is used in virtually every aerospace company in the world, has information on that topic too. There is an entropy function, much like the energy entropy function, but it operates on information. It measures how much scatteredness there is. In other words, there's quantitative measures that we don't have to wonder whether or not what we're looking at is random or it's structured. We can tell, and by how much it is. All life structures need information. The DNA code for the proteins for the DNA. And I ask you a silly question. How is that going to occur when you might only have one of them at most? Also, there has to be a translation, a language to get that transcription to occur. And all these are mysteries. Nobody knows the answers to these things. This is a picture of Merrill Skolnick himself and the latest edition of his handbook. I'd like to close this section by asking, in response, can anybody identify any of the scientists pictured in this slide? Any of them at all?
Is Newton in red?
No, he's not in red.
The second one is Newton.
The second one on the top row is Newton, that's correct. Any others? They are all very famous scientists. If you have any training in science at all. Pardon me?
Pascal, is he in there?
No, neither one of them is in there. Good guesses, but they're not there. Anybody want to take a guess at that first one over there? Does that ring any bells? By the way, these are more or less in chronological order too, from left to right and from top to bottom. Go back to about 50. Huh?
Did you put Edison in there? Edison?
No. No, he's not in there. This only goes to the end of the 19th century. And he's more known for being in the 20th, although he lived in the... Yes?
Pasteur and Galileo in there?
Okay, if they're there, where are they?
The upper left is Galileo, and the lower left is Pasteur.
No, the upper left is not Galileo. In fact, he's not in the picture. But Pasteur is one of the pictures. Which one? I said they more or less go in chronological order. Think back about your history, when these people lived, if you know that. One of those people is Pasteur. Which one of them is it? I'm not going to kill you if you get the wrong guess. Anybody want to take a guess?
Bottom left.
Bottom left. No, not quite.
Top right.
Nope. It is. It's the center lower. That is Louis Pasteur, a picture thereof. Let me go through the rest of them then, unless you want to try any more guesses. Any? Okay. Yes?
Okay, is Kepler or Copernicus in there?
Kepler is there. Which one of them is it?
You got the top left.
That top left is indeed Kepler. There's no Copernicus in this. That is a picture of Kepler. It's kind of known. So we've got, what, 3 of them now? That leaves us with the 2 on the right on the top and the 2 on outside and the bottom. Any guesses on any of those? We have this great brain trust here. I'm sure that these names would sound familiar with all of you when I mentioned them. All right. The third one, the one in red, is Carl Linnaeus, known for taxonomy. In fact, somebody recently said that he had greater influence than Jesus. I don't know that I would agree with that, but it's been recently said. Ironic because of the fact he's in this set of photos. The one on the right, on the top, is the greatest experimentalist of all time. He only had a master's degree. And yet, most of the electronic devices you have in your home, in your car, are due to that one individual. Without his contributions, we would not have any of them. Who is it? Who, oh, who could it possibly be?
Galvani.
Nope. Nice try. He was an Englishman. Michael Faraday. Should have gotten that. Okay, how about the ones on the outside of the bottom? The one on the left is James Clerk Maxwell. The one on the right, Lord Kelvin. We know him for his temperature scale, the Kelvin scale. What else did these men have in common?
Not believers.
Close. They were not evolutionists. Some of the founders of modern science were, but none of these 16. Notice some of those names. In fact, you might recognize all of those names if you had any science at all to speak of. These are the references that I used in part or in whole. The only ones that are not secular are the ones in green. All the rest of them are standard textbooks. I pointed to many of them in this talk. I want to give some credits where they're due. Joel Emilio for a lot of the slides, Tom Canfield in the back, and Chad Williams, who's a former Navy SEAL, was responsible for part of one of them. The end. We ran into about 8:30 now, didn't we? Okay. Does that give time for any questions, Mike? Sure. Okay. We had a question, I believe.
I was wondering, I kind of lost my train of thought already, about the L and D, and if the R group, the side group, was big enough to make one face more approachable than another, and that would make it L or D.
Well, there have been actually experiments done on what happens if the R group is the same to try to determine whether or not one of them is preferable to the other, but there's been no progress made. And I remember even hearing about that when I was in biochemistry many years ago. The question is, why when they are completely symmetric? See, that's the point. They are mirror images, so they are completely symmetric. Let me hold that hydrogen up there. Now you can see the R group. See, that's completely symmetric.
Is it because of the enzymes that put it together? There's like kind of like...
What we have right now are the amino acids, and by the way, enzymes are proteins. They're formed in the same way as any other protein is. They would have the same problems, therefore, of why is it only L instead of any Ds. See, my problem is the symmetry has to be broken somehow, and how is that to occur? I read a 300 and some page textbook that claimed to do so, starting with the non-parity of particles. I'm not convinced. I think it is too fanciful. I'd like to get hold of that textbook again just to get its title. See, that's the mystery. This is why Isaac Asimov said what he said. Just happened one way or the other. Any other questions? Yes?
I don't know who you are. I'm sorry. Could you tell me who you are?
My name is David Dana-Bashian, and my name was printed on the first slide.
I saw that, but I mean your qualifications for that. Did you?
I have a bachelor's and a master's in math and a bachelor's in chemistry, ACS certified from Purdue many years ago. I have 205 semester units, 68 of them in math, 55 in chemistry, and 13 in physics. And in case you're wondering whether or not I was the real thing, this is a copy of the Register. This is the official publication of Phi Lambda Upsilon, the honorary chemistry fraternity. I'm a member of this organization. It's a badge I wear proudly, despite being mostly a mathematician.
Another second question.
Yes?
You, Ross, talked about the recent findings or discoveries on the moon that would cause a lot of questions to be asked about the existence of God. Are you familiar with what he's referring to?
Not particularly about the moon. I just have enough of my own concerns, as you saw. And they're pretty elementary concerns, and usually Hugh Ross would try to dismiss them out of hand. I went to their organization to see if they had any problems with some of the other topics. And they were more pressing to me than asking about the moons. Well, if he has anything to contribute, fine. I just wouldn't trust him in general, because what else he says that I know is folly. I mean, I'm a scientist too, and I know where the weaknesses are. I also know that he's quite inscrutable to read. I can read almost anybody else that's an old earther, but not him. He also has some extremely fanciful theology as well. The Rocky Mountain Creation Fellowship pointed out a number of the things that he said a number of years ago. They're too unbelievable for anybody to say, but he did say them. And they're just nonsense. Yes. Any other questions? Yes, another.
I vaguely remember on the news / the internet something about gravitational waves and something to do with the Big Bang, and I wasn't very caught up on it.
Yeah, that was a supposed discovery announced around the 17th of March this year. This was to try to patch the hole, so to speak, and to try to come up with why the hyperinflation. Alas, it was conceded around the 3rd of May that the data may not have been examined very well and in a very elementary way. So not only is the jury out, but it may be out for quite a while. And Danny Faulkner from University of South Carolina, Lancaster, pointed out when this supposed discovery was made that it was probably going to fall by the wayside as other similar discoveries of sorts had already been in the recent past. It looks like his prediction about this one falling away is going to come true as well. But we are empiricists. If somebody wants to come along and present new data, new methods, new everything, better ones, great. Let us not be the ones to stop the discoveries. Another question. Yes?
I was going to ask you, how do you feel about the astronomers right now trying to take away Pluto's status as a planet that relates to it?
That's just a category distinction. I could care less what they call anything, frankly. What matters to me is what is the behavior of it, not what name is it called by. The fact that it happens to be small and 17 degrees out of phase with the rest of them doesn't prevent other things from being asked about it. Like, for example, where does its moon come from?
Yeah, Charon.
Yeah, the moon is some 30 to 40% the size of Pluto. Try to blast Pluto to get a moon and you'll probably blast Pluto out of existence. Another question, yes?
intelligent design, is there more leaning toward that philosophy or the scientists?
I think ICR put it very well, and that is, where's the intelligence going to come from after all? Why not just go all the way and not stop halfway between things? I've been raising all sorts of questions. You could inject ID all you want to it, just at those points. But I would say instead, and more further, that the things that I have mentioned, particularly as you see on this review of the list, 6, 8, and 10, are finger marks. That there isn't just a chance occurrence or some nebulous outer space alien causing things. And by the way, where's the outer space alien then? See, things derive or devolve back to the point there has to be an original spiritual, not physical existence, because spirits are not subject to the laws of thermodynamics, among other things. Anything that's material, notice that I'd already ruled out all the causes. It's all subject to thermodynamics, and it doesn't have enough motivation or force to do anything after a while, let alone be the cause of everything.
Okay.
All right?
Like that, I think maybe you didn't understand the question.
Okay.
I'm just wondering, in the scientific community, are we leaning more toward intelligent design than we have in the past?
Are we any what, please?
Leaning more toward the idea of intelligent design than we have in the past.
Well, you might say the evidence might lean more that way. Unfortunately, the humans are going the other way. They have the court case in Lancaster, Pennsylvania, was it 1999, that essentially shut down the whole thing from having any influence in the schools by saying, in effect, and the judge was very reprimanding the ID side, saying, in fact, you lied deliberately. Well, that was his opinion, and unfortunately it carries the weight of law. But things have essentially, so it's more or less relegated to a corner. And other groups like ICR and AIG don't really side with the ID movement either, because it advocates, among other things, an old Earth. At least the people within it do. It tends to get some airing on Greg Kogel's program on Sunday afternoons. But yeah, any other questions we have here? Did I answer yours?
Yes.
Okay.
What were the numbers that you said were the most?
I like 6, 8, and 10 the best myself. 6 and 10 are really nice because nobody discusses them. Very few people even know that those are issues, but they are powerful issues, I would contend. Not just because they're not being discussed, but because of the implications. However are you going to get that carbon to the Earth to form those coal beds in such concentrated form from granules? By the way, particles do not compactify on their own, whether it's forming moons or forming coal beds. It's bad enough to try to get bituminous coal, let alone anthracite coal, buried deep in the earth by the only process that's ever been put forth by the people on the other side of the aisle, and that would be the triple alpha process. Yeah, do we have any other questions here? Well, if not, I want to thank you for coming, and perhaps Mike will have some slides from us later.
Slides?
Well, I mean the prints.
Oh.
Yeah.
So they might be able to publish what you put together?
Oh, you can do whatever you want, because it's a freely given talk, and
I just have to get it on a data stick from you.
yeah, we'll get you to get a data stick for this to do that. Okay, yes, you have another question?
What about the video, or maybe in a PDF form, or the slides? Or is there any way we can
Talk to Tom about that. And to Zell, who's making an alternative from the side here. So there are actually two of them going on at the same time. Another question? All right. Well, thank you very much. And by the way, you can also see 4 of my previous talks on YouTube. They go under the same title, 16 Nearly Impossible Issues for Evolutionists to Answer. There's also a spoof of my video out there, too, somebody decided to do. It's poorly constructed, unfortunately. You can also go to the Backyard Skeptics website and see that I was the presenter on the 17th of June in debate number 9, and I was also contributing to another debate, the one after that point, on July 23rd, but its video has not been posted yet. So I do other things as well. Yes?
Is there a website you refer people to if they wanted more information other than your own?
I don't have my own, I only have YouTube. That's what I would, that is, you mean other information besides the information that I presented?
Well, not other information, just in general, if somebody has questions about evolution and creationism.
What would be one you would recommend?
What?
I don't know that I don't want to be egotistical about it, but I don't know of any to recommend other than the things that I've said. This is why I'm saying them, because nobody else is saying them. And I think they're actually more powerful than the things that have been. The things that have been tend to devolve into artistic arguments. Well, anthropology is horrible for this. You can see whatever you want to in a skeleton, I guess. But this is hard and fast, dry science that has repeatability, testability, publications galore, where nobody disagrees with the essential facts about the matter, especially the mysteries. I'll conclude that they're mysteries. It's just who wants to try to solve them with only material.
Okay, and how would you find them on YouTube?
You would just type in those words, those 8 words, and up near the top will.
Oh, that was okay.
That's right, those same 8 words. You might try typing my name, but that could be even worse. And you might get other things too. But that's the method I have recommended. Is foolproof, and my stuff will always appear at or near the top of the search list by just typing those. You might actually get there by typing even the first few words of that, but I wouldn't count on it necessarily. Somebody else might pull up spoof later.
And that covers what you've covered tonight at YouTube?
These are earlier versions of this same talk. They were given on 9 July 2013, 10 August 2013, 19 October 2013, 15 February 2014, and 26 April 2014 is not available. Okay, you're welcome. Any other questions? All right, and thank you very much.